Welcome to this video. In this video, I will be discussing regarding the derivation of generalized Gibbs state. So I have discussed Gibbs state in this series of these videos previously also. So here we will be looking at a derivation of this state. This state is particularly important when we discuss about these thermodynamic resource theories and how these finite dimensional systems they make transition from one system to another. In those cases, this state is essentially treated as a free state, and we say that we have access to this state. We can use it as a state that can be used again and again. Even in the notion of passivity, these Gibbs states are called completely passive. What that means is that you cannot extract work from these states, from the Gibbs state. Howsoever you go to increase your dimension using the tensor product, you cannot extract work even if you like. Suppose you have a Gibbs state tau. Then these states are generally associated to what we call thermal baths, and further these states, even if you take k copies of this state, then also this state can't be used to extract work. This is also gives us the classical picture, the classical notion that thermal baths, they thermalize a system, they don't contribute to work extraction properties. So with this, let's try to derive such a state. So what is the notion? So we try to find a state. Now a state is a density matrix, so it must be diagonalizable such that the eigenvalues sum up to 1, such that this state maximizes the von Neumann entropy, that is minus trace log rho log rho, subjected to the constraint that average value of two observables are fixed. So these observables can be anything. They can be energy, they can be number of particles, they can be angular momentums, anything. So subjected to the constraint that the average value of these observables, here we have taken two observables, but we will see that it is generalized to n observable, subjected to an average value, that this is the average value of these observables. This average value is fixed or it remains constant, and these are the constant values. So here we see that we are getting two constraints here, and already sum of probability is 1, or the trace of this rho state, as it is a density matrix, it must be 1. So we have three constraints altogether, and using these constraints or abiding by these constraints, we have to maximize the von Neumann entropy, and the state that performs that maximization is the Gibbs state. So that is a very precise definition of Gibbs state. Now there can be a problem, that is these quantities, that is y, z, they may not commute with each other, and they may even be diagonalizable in different bases, and that basis may differ from the basis where this is diagonalizable. To tackle with this problem, we present an important theorem that actually shows that we have to take a particular basis. I mean, this rho automatically needs to abide a particular basis even to maximize this entropy. So that's what we will see now. So it essentially follows from the fact that you see, when we have coherence in our system, that is the off diagonal terms, if we ignore the off diagonal terms, that is we reduce a system to only the classical states, then automatically the entropy of the system rises. So even if you have a basis where there is off diagonal terms, essentially you can just ignore the off diagonal terms and take the diagonal terms, and that will automatically rise the entropy. It's like act of forgetting information rises the entropy. So that's what we will see in this particular instance now. So we start by Ulmar's theorem that I have previously discussed. So it says that, so rho majorizes or is majorized by this sigma. That means in probability space, majorization is just a this is just an ordering. So rho majorizes this sigma. I have also defined majorization in my previous videos. it implies that sigma can be written as a unital mixing of rho. So this is a particular channel which is called a unital channel, and these are the unitaries, and the unitaries are applied on this rho with certain probabilities. So it is a probabilistic mixture of unitaries acted on the system rho. And here we have an implied sign, and this further implies that there exists a channel, a quantum channel, that takes rho as an input and gives sigma, such that this channel is essentially bistochastic channel. So this implies sign follows all the way, and I am not proving the formula or like how is this derived. I may prove it in other videos, but what is important is this majorization condition is related to unital mixing, and which is related to a bistochastic channel. And what is a bistochastic channel is quite easy to understand. In the cross operator representation, it means that the channel written in cross operators form, E and E dagger, these are the cross operators, it must satisfy first, this is the completeness criteria, and this is the second criteria that makes it bistochastic. So this is called, it keeps the identity element fixed. A bistochastic map keeps the identity element fixed. So these both conditions, if they are satisfied, then we say that this channel is a bistochastic channel. So here you see these constraints needs to be satisfied, but one must remember that here this E need not be a unitary operator. It just needs to satisfy these particular constraints. So with this understanding of these Ulmar's theorem, we go to one more variation of Ulmar's theorem, which is called Schur-Horn theorem. It particularly says that if we take a rho and project it, that is like taking only the diagonal terms of rho, this rho may be a non-diagonal matrix, but we take the diagonal terms by projecting it, and you name this matrix, this entire operation, as sigma, then automatically what it means that these projector operators, they satisfy these both conditions, and that means projection channel or non-selective measurement channel is essentially a bistochastic channel. And what it means is that we have the majorization condition. So you see here the majorization relation will look something like this. But in turn what it means is that this majorization relation, if we take this concavity property, sub-additivity and concavity of von Neumann entropy, that means that if rho majorizes sigma, it implies that S of rho is less than S of sigma, because sigma is like in some sense a more random operation. Sigma is the unital mixing of this rho. You can also like take S on both sides and use the sub-additivity and concavity of von Neumann entropy to prove this. So with this we have understood an important fact, that is, if we diagonalize, if we dephase, this operation is called dephasing, that is only looking at the diagonal entries of rho in some basis, that will essentially increase the entropy. And that is what we intuitively understand when we say that ignoring the diagonal terms, ignoring the coherences, essentially increases the entropy of the system. So with this small understanding, we now try to perform the maximization to find a state that obeys these conditions. So remember, our main job is to find a state rho that maximizes the von Neumann entropy, abiding these constraints of average fixed energies or average fixed values of two different observables. These values need not necessarily be energy. They can be number of particles also, or values of angular momentum, anything. So you see, essentially we have these three constraints. These are the constraints, and now we use the Lagrange's method of undetermined multipliers, which says that you have to maximize this particular function S of rho. So you take this function and introduce the Lagrange multiplier, this beta, these beta 0, beta 1, beta 2 are the Lagrange multipliers, and then inside the Lagrange multiplier put whatever constraint that you have. So I have put these three constraints here. Now you have to just take the derivative, and we will soon see what this lambda j is actually meaning. So from this to this line, now we will just club these coefficients and use the fact that c1, c2, 1, these all are constant number. So these are constants, and we can remove them, and essentially we get such a equation. So now here comes the important point. We say that rho needs to be diagonal. Rho needs to be diagonal in the basis of this entire operator. You see, this is not only y operator or z operator. This is a particular combination of y, z, and in this basis rho must be diagonalizable, because whenever rho is not diagonalizable in the basis, I can still maximize the entropy by removing the off-diagonal terms, because S always increases on performing such a projection. So with this understanding, we now go to a basis, these lambda j. Hence, what it means is that these lambda j is the eigenvalue. It is the eigenvalue associated with rho in the basis in which this is diagonal. So here I have written it in that basis, and here the trace is also written in the basis, and then this is the trace of rho times oi. So basically, what is oi? Oi is the, if this is the operator, this operator can be written as summation over I oi times lambda I, and rho can be written as lambda I times lambda I. This is what is the claim that dephasing operations or decohering your system increases the entropy. So hence we have to just perform this derivative, and that's easy to perform, and we will get the values of these eigenvalues for such a state that is maximizing the von Neumann entropy subjected to those conditions. Now once we have obtained these lambda j's, what I have written in this particular box. So here you see this oj is also there, which is the eigenvalue coming from this operator. So once we have that, these lambda j's, they must satisfy this summation over I equal to 1, because a trace of rho will be 1 and trace is basis invariant. So that essentially says that e power minus 1 plus beta 0, that is this part, is 1 over summation over j e power oj. And this is what we call as 1 by z. Now you see, already we are getting the notion of this partition function coming out. So now with this, we have almost done all the necessary things. So finally what we have? So finally we have a probability distribution lambda j that is in this form, and e power, this particular term can be written as 1 by z. So the state that we required, now I am calling it tau, this is the maximized state, it is this particular state here. So here we know what is z, z is simply summation over j e power minus oj, or it is the trace of e power minus o operator, or in other words, this oj are the eigenvalues of this operator o, and this operator o is a weighted sum. It is a weighted sum of all the conserved operators with the weights which are precisely the Lagrange multipliers. So with this understanding, we have finally been able to write the thermal state or the Gibbs state. And you see, while writing this state, we automatically saw that the notion of partition function coming out, and the notion of beta, that is 1 over temperature, that is also coming out. So this is the thermal state, e power minus summation over I beta I ai divided by trace of this entire thing, so that this is normalized to 1, and the trace, so the trace of e power minus summation over I beta I ai, this is what we call z, or the partition function, and here beta are the Lagrange multipliers. So with this understanding, we can say that if the conserved quantity is the Hamiltonian, the Lagrange multiplier is 1 over temperature. Further, you can go to this grand canonical ensemble where the free energy, where we have the free energy written as average of the Hamiltonian, average of number operator, and the entropy. Here you can see the Lagrange multiplier beta for this number of particles which is conserved will be mu over T, which is essentially the chemical potential divided by temperature. So now we move on to understanding of a new notion which is called free entropy. So we know what is free energy is. That is these quantities minus T times S. And here, as we can see that this energy or the Hamiltonian operator here has been given a special position because you have shifted the Lagrange multiplier from the Hamiltonian operator to this entropy, but you have kept the Lagrange multipliers associated to other constraints like the number operator constraint. So what we plan to do is that we plan to shift this this Lagrange multiplier back to this place, and hence we define a new quantity that is called free entropy, that is written in this form: summation over I beta I, expectation value of this operator, where these are the operators over which we have the constraints, like their average value is fixed. So it is the expectation value of this operator minus the entropy of the system. In this particular definition, this entire thing is called free entropy. And here we can see clearly that free entropy keeps each of the conserved quantities in an equal footing by weighting them with a particular Lagrange multiplier. But here this was not the case. So in some sense, free entropy captures more about our system than this free energy, and it plays important role in transition of states. And further, we can prove some of the properties of this free entropy because we can easily calculate these averages. So the first property that I try to prove is that suppose we calculate the free entropy of the Gibbs state. So this is the Gibbs state. We calculate the free entropy. So what we need to do is that we just write the first part as it is, summation over I beta I ai, and then here the entropy. So remember, entropy of a state rho is simply minus trace of rho log rho. So here instead of this we will just put the thermal state that I have here, this lower part is simply Z, the entire denominator is Z. So I can put it here, the thermal state, and it will simply become in this form because you see here I have log of the state that will be this particular thing divided by I will have Z, and the Z part will separate out, like ln A by B will be ln A minus B, and we can get this, and essentially it will give rise to just the partition function. You see, this is very similar to the fact that we have in statistical mechanics. We have a minus beta f, where f is free energy is log Z. This is the remnant of that fact, but here you can see that beta is no longer appearing because this is free entropy, not free energy. So similarly, we can do one more calculation. Minus trace rho log tau can be written in this particular form, and we can add these two equations. And finally, I have done it explicitly here. We just add this quantity in both sides, minus S of rho, that is entropy of our state. And what we can prove? What we can prove is that the relative entropy of our state with respect to the thermal bath is simply the difference of the free entropy of our state minus the free entropy of the thermal bath. So the free entropy is like is providing a measure of this relative entropy. So that's all for this video. In this video we discussed making of this thermal state or the derivation of this Gibbs state. We discussed what this free entropy means. So that's